Good morning, everyone. It is a great pleasure to introduce Professor Costello as the ISR Distinguished Lecturer for this academic year, one of the few lecturers, several lecturers. Professor Costello received his PhD degree from the University of Notre Dame. He returned to Notre Dame as professor in 1985 and has been there ever since. In the year 2000, he was appointed the Leonard Bettex Professor of Electrical Engineering. He received numerous awards, including the IEEE Third Millennium Medal, the Donald Fink Paper Award in 2009, and just this year a Joint Information and Communication Theory Society's Paper Award. For his work on a new class of error-correcting codes. He gave a fascinating technical talk about this class of codes yesterday. Today he's also an author of a popular textbook on coding theory widely adopted, which is now in its second expanded edition. Today he's giving a historical overview of coding theory in its relation to communication, and fittingly for a professor from Notre Dame, the title is Genesis of Coding Theory, and they already anticipate the second installment, perhaps Exodus, and so on. Okay.
Thank you very much, Sasha. Sasha mentioned the expanded version of the book, and I said much expanded. The original book was 600 pages, and the second edition is over 1,200. So it takes you have to have a briefcase to carry it around any place. So I just realized something I should actually have on my cover slide. I don't even. Sasha mentioned that I was the Bettex Chair Professor of Electrical Engineering at Notre Dame, and Mr. Bettex would not be happy probably if I didn't have that. I should put that on the slide. He also mentioned the genesis of coding theory. So being at Notre Dame, which is a Catholic university, you can get away with having a talk which has a little bit of a biblical title. And there's nothing very heavy about this talk. Okay, it's Friday, so that's good. This is a kind of a light talk. It's a historical talk. Coding theory is something that's been around for a little bit more than 60 years. And there's a lot of well-known people who have worked in and out of this area. And what I do in this talk is just kind of go back to the beginning and trace the kind of development of coding theory, and in particular focus on kind of practical codes that wound up being used in practice. I don't go into all the different false leads that many of us have taken over the years, but focus on the developments that occurred that really kind of impacted the field and impacted the practice. And again, not from any deep theory viewpoint, but just here's how things developed and here's how progress was made. One of the really nice things about coding theory is we started with a goal. We started with channel capacity given to us, handed down from on high by Claude Shannon. And so we kind of knew where we were going. And so this talk kind of tracks that progress over a 60-year period. So I've had a lot of good students over the years, many of whom have helped me put together this talk. So in the beginning, there was Claude Elwood Shannon. And this is what now I will focus here for those of you that have had some background in communication systems on the so-called additive white Gaussian noise channel. This is the standard channel model for digital communications, the one that most people use. It's not the only channel model. There's all kinds of other channel models which we have to deal with in practice, but almost any digital communication system has an aspect, it has additive white Gaussian noise added to it. So this is typically the channel model that people use to in order to design coding and modulation systems. So this the coordinates here in this picture, which I'm going to use throughout the talk, it's basically power efficiency versus bandwidth efficiency for a digital communication system. Power efficiency, which we usually call signal-to-noise ratio, it's just the channel quality, ratio of average information symbol energy to single-sided power spectral density of the noise. And that's a little bit technical, but if you know this, you know this, and if you don't, it's just signal-to-noise ratio, which everybody knows when they kind of turn on their cell phone anyway. And it's usually expressed in decibels, in dBs. Okay, and so it's a log scale. And the y-axis is bandwidth efficiency, and this can be normalized kind of in different ways sometimes, and it's just a choice that I made here is normalize the number of information bits transmitted per two-dimensional signal. So those of you that know a little bit about modulation, if you know what like 8 PSK or 16 QAM or something, those are all two-dimensional signal constellations, and the number of bits which you can transmit per two-dimensional signal is the units of bandwidth efficiency that I've chosen here. And for example, uncoded, if we're not even talking about coding, but we have an 8 PSK signal constellation that looks like this. These are 8 possible modulation symbols that could be transmitted in a given symbol period. And since there's 8 of them, it can represent, you can use 3 bits to choose which of the 8 signals you're going to transmit. And so the bandwidth efficiency of this system would be 3 bits per two-dimensional signal. And if you have a 16 quadrature amplitude modulated signal set, which you'd have to choose one of these 16 signals, you would have a bandwidth efficiency or a spectral efficiency, sometimes called 4 bits per symbol, or 4 bits per two-dimensional symbol. And then Shannon's theorem says the following. It says, I mean, this is one way of presenting it. You can write the expression in several different ways. This is just the most convenient way for this talk. It lower bounds the channel quality, namely the signal-to-noise ratio, for which there exists a code that can achieve arbitrarily reliable transmission. Now, what do we mean by arbitrarily reliable transmission? Well, you tell me. Okay, if reliable to you is 10 to the minus 5, there would exist a code, if it meets this bound, that could achieve that. If reliable transmission for you is 10 to the minus 10, there will also exist a code. We're guaranteed to be able to find a code which will achieve that. 10 to the minus 15, 10 to the minus 20, whatever. It's not going to be the same code, but we'll find one. Okay. And for the additive white Gaussian noise channel, this lower bound can be expressed by this. So this is simply our signal-to-noise ratio, our power efficiency on this axis, as a function of our bandwidth efficiency on this axis, so it gives us this curve. So we wind up with kind of everything to the right of this curve being possible. There's a converse to Shannon's theorem. So everything to the right of this curve is possible, and everything to the left of this curve is impossible, as long as your requirement is that you be able to communicate with arbitrary reliability, as low a bit error rate as you want. So this is the so-called coding theory playing field. I mean, codes can be looked at as points. They have on this graph, they're going to have a certain bandwidth efficiency and power efficiency. And the closer they are to the capacity bound, the better they are, in some sense, in terms of being able to correct errors during a noisy transmission. And now the capacity bound assumes that you can use any kind of modulation that you want. It doesn't really have to be digital modulation. It could be a continuous alphabet. In practice, it's convenient most of the times to use a digital modulation alphabet. Something like BPSK or QPSK or 8PSK or 16 QAM or whatever. And these, when you choose a modulation alphabet, you lose some flexibility in terms of designing the overall system. So the capacity, if you like, of these fixed modulation alphabets is somewhat less than the overall capacity bound. For example, if you're going to use 8 PSK, you can't get 6 bits per symbol. Because there's only 8 symbols, you can only pack 3 bits into them, and that's without any coding. So each of these modulation alphabets has its own capacity. So if you say you're going to choose the modulation alphabet for practical considerations, then you would be measuring against this. And okay, I think I just said that. And so, for example, if you're using BPSK or QPSK, your coding theory playing field would be this area down here. With these modulation alphabets, you can't get more than 2 bits per 2 dimensions, two-dimensional signal set. So, and a lot of the early applications of coding are in this range, so this is where we're going to look at, but we will focus on the higher bandwidth efficiency range during part of the talk. There's also something called the cutoff rate bound, which I think I'm not going to dwell on. Basically, it's a bound that comes from a union bounding technique rather than a Chernoff bounding technique. And if you understand what I say by that, then I don't need to explain it further. And if you don't, you got to go to Professor Barg's class, and he'll tell you. So this is just a weaker bound. Okay, it was considered the practical limit of coding for decades. A lot of us fell into that trap. We thought, well, we're never going to get to capacity with anything practical. Maybe we could get this far. Turned out to be a false lead. Now, what I'm going to do here is just to try to compare and see how different codes developed over the years. I'm going to assume that we're happy with 10 to the minus 5 bit error rate. This is, in many applications, 10 to the minus 5 is kind of a target bit error rate, something in that range, 10 to the minus 4 to 10 to the minus 6. So some applications like storage and optical and stuff like that, they require lower bit error rates than that. But this is typical for many applications. So we're going to say, rather than showing what power efficiency, say, we need to get 10 to the minus 20 or something, we're just going to show what power efficiency we need to get 10 to the minus 5. Okay, so this is the average decoded information bit error rate. And these points are what you can get without coding. So this is where the field of digital communications was before Shannon's work. So, for example, uncoded 8PSK, that would be this point, required 13.2 dB to achieve a 10 to the minus 5 error rate, and it got this spectral efficiency, 3 bits per symbol. And similar with 16 QAM required 13.9 dB to get 4 bits per symbol. Now, this uncoded 8PSK, now, how good was that? Well, it was 10 dB from capacity. Otherwise, here's the capacity here at 3 bits per symbol, and here's what 8PSK can get without coding. So there's a 10 dB gap. Okay, and that's what coding tries to close, is close that gap and see how close we can get to capacity. So there's also, this is a point that can make briefly here. If your requirements are stricter, for example, 10 to the minus 10, then you require larger signal-to-noise ratios. I mean, this is just, in a sense, common sense. If you want better performance, you're going to need more signal power. Okay, that's all I'm saying here. And 10 to the minus 10 is better performance than 10 to the minus 5. And in the case of 8PSK, you require now 16.8 dB to get that, whereas the previous, so this uncoded gap to capacity now, instead of being 10 dB, is now 13.5 dB. Okay. Remember, Shannon said no matter what this is, you should be able to operate right over here at capacity. So here, if your requirements are 10 to the minus 10, there's 13.5 dB to be gained potentially, in theory, from coding. Okay, so the first day of creation here was, say, I just jumped 10 years to 1958. And as I said, most of the slides are focusing on this lower end here, the lower rate end, and all the original coding work was done in this range. I mean, it was thought for years that coding wasn't useful at higher bandwidth efficiencies. It turned out, again, that turned out to be wrong, but we'll see that later. So Richard Hamming was the one who invented the first error-correcting codes. He invented, I mean, this is just 3 examples. These are so-called block codes, which have a couple of parameters, n and k. N is the block length, number of bits in a code word. K is the number of information bits or symbols in that code word. The difference is the parity bits, the parity-check symbols. And k over n is called the code rate. And we will indicate these various points. A square point means that a code is decoded using hard demodulator decisions. So in a digital communication system, you have at the receiver, you have a matched filter, and every symbol time at the output of the matched filter, you take a sample. And it's a real number. But you, in order to process that, if you want to build a somewhat more expensive decoder, you can process the real numbers directly. But if you want to simplify the design of the decoder, you can quantize those real numbers. And in the limit, I mean, the most you can quantize them is just quantize them into binary, 0 or 1. Okay, and that's called hard quantization. That makes for the simplest decoding. You lose performance when you do that. I think it's it's intuitive that if you quantize a real number into one bit, you're losing something. So, but for reasons of, as I said, the points I'm kind of putting on this graph are points that were actually could be done in practice at the time. Okay. In the 1950s, this was what was possible, is hard demodulator decisions with also codes that are of kind of very short block lengths, 15, 31 here. And so what do we gain? Well, this rate, 26 over 31 Hamming code, notice compared to uncoded BPSK or QPSK, it sacrificed bandwidth efficiency. Okay, that comes from the 5 parity bits in this code. But it has a coding gain of a little more than 1 dB. So this 10 dB gap is cut down by a little more than 1 dB by Hamming's original work. And then there was a Swiss mathematician by the name of Marcel Golay. I know there's some mathematicians in the audience. A lot of mathematicians have worked in coding theory over the years. Mathematicians, electrical engineers, computer scientists primarily. Marcel Golay invented a very, I have the 2412 version. Those of you that know coding theory know that there's a 2312 version. I just wanted to plot the rate of half. That had over a 2 dB coding gain with hard decisions. And the 2312 version anyway was a so-called perfect code, which the mathematicians love and the engineers love too. But I won't say what it was. The rate, now there's also a Reed-Muller code in this time frame, which was a low rate code, which gained about 1 dB. So the Reed-Muller code, notice it gives up a lot in spectral efficiency, only gains 1 dB in bandwidth efficiency, in power efficiency. So in some sense, these are better codes because they're also gaining a dB, but they're not giving up nearly as much in terms of spectral efficiency. Okay, and basically I'm not going to show too many of these 10 to the minus 10 points, but basically what happens at 10 to the minus 10 is all the points move to the right. Again, you need more signal-to-noise ratio to get a lower error rate. So for 10 to the minus 10, the points all move to the right. And so the coding gain actually is greater. That's because the uncoded point also moved to the right. Okay, and the coding gain, so that the code wasn't hurt by the more stringent requirement of moving from 10 to the minus 5 to 10 to the minus 10. That didn't penalize the code quite as much as it penalized uncoded modulation. So the coding gain actually is about a half a dB better in this case. I won't dwell much on 10 to the minus 10 in the talk because the story is pretty much the same. You need the points move to the right, the coding gain improves a little bit. Okay, the second day of creation, 1968. So here I'm going to use in the green points are the new ones. And some algebraic, a lot of work on algebraic coding was done in this decade. And I just mentioned a few of the things here. The so-called BCH code. This is a 3116, I think, and here's a longer one, a 255, 123. All kind of rates around a half, just so I picked those rates kind of so we compare them with other rate of half codes as we go through. It's a popular rate, too. A so-called quadratic residue code, which is exactly a half. There are many people who worked in this area, and not being comprehensive or necessarily even fair here. For example, neither B nor C nor H has his picture showing here. Okay, but these are people that designed the codes, but these are people that more worked on the decoding, solved the decoding problem. So there's two aspects to coding. You got to design codes with good properties, but then you got to figure out how to decode them. And the decoding is sometimes the harder problem, or often the harder problem. These guys also, B and C and H, were mathematicians. Okay, these guys were engineers, so you can see my bias. All right. So Elwin Berlekamp, Tadao Kasami from Japan, a young version of Shu Lin here, who's my co-author on the book that I wrote, and Wes Peterson, who passed away a year or two ago. This field is mature in the sense that some of the early contributors have passed on. And Wes had actually the earliest book in coding theory. He co-authored with one of his students, Ned Weldon. And these are people that contributed a lot to algebraic coding. You can see that the coding gains here are getting more substantial, 3.5 dB. A lot of that is because we're simply using longer codes. I mean, the thing that I didn't mention about Shannon's theorem is to get to capacity, you have to use long codes. Otherwise, it's an asymptotic result as code lengths get large. Now, you say, well, okay, why don't you just take this code and make it 1,000,000 bits long? Well, I'm trying to show in this development here what was practical at the time. And code lengths, just because of implementation limitations, code lengths like this were considered practical and were implemented in actual systems. So this was what could be done, and you could get 3.6 dB coding gains. So we'll see is that part of the story is, which I don't emphasize so much because I'm not a VLSI person or anything, but part of the story here is, again, simply Moore's law operating, that as the technology develops, we can build more complex decoders, which means we can decode longer codes, which means we can get closer to capacity. So it's not all coding theory which contributes to the gains here. Now, another very important code that came in during this decade was these Reed-Solomon codes. And I show them two different Reed-Solomon codes here. Irv Reed and Gus Solomon, both of whom have passed away. Irv Reed recently. And these are important because these wound up, although they're non-binary codes, so they're codes constructed over high-order Galois fields. And I think it's true that I believe both Irv and Gus have said this, that when they invented these codes, they had no idea they would be practical. Okay, they were non-binary, non-binary things are typically difficult to implement, but they had nice coding theoretic properties. They were an interesting class of codes. They're in some sense a generalization of these BCH codes, so it was kind of, some more theorems that people could prove. But it turned out they were tremendously practical, as often happens in research. Something you think nobody's why would anybody ever possibly be interested in this? Well, sometimes they are. And these are the codes that are commonly used in compact discs and CDs. So every CD has a Reed-Solomon code buried in there. I remember Gus Solomon going into, telling this story that he went in to buy a CD once, and he goes up to the counter and he says something, I don't remember exactly how the story went, but can you tell me something about the CD? And the salesman at the counter, young fella, said, oh yeah, these are really neat, and they've got Reed-Solomon codes in here. And he said, well, so Gus said, well, what's a Reed-Solomon code? Can you tell me about it? And finally, after all this, and he's going to sign his credit card or something, and he signs Solomon, he says, and the teller said, oh, you're Solomon, yeah. So he loved to tell those kinds of stories anyway. So, yeah, so I've said that. Now, the reason they're used on storage devices, storage devices often have errors which are clustered into bursts or something like that. And then the non-binary byte or symbol-oriented nature of Reed-Solomon codes is nice for picking up clustered or bursty errors like this. So, yeah, said that. Okay. And then convolutional codes were developed. Actually, they were developed back in the late 50s, but they became more popular here. Peter Elias is the original developer of a convolutional code. Jim Massey, who was my thesis advisor at Notre Dame, was one of the early workers in the field. And they're defined by 3 parameters. There's an extra parameter rather than n and k, called the constraint length, nu. And it basically is the convolutional encoder has memory. The block encoder does not. So you can think, a block encoder is just in terms of logic, digital logic, it's a combinatorial circuit. And convolutional encoder is a sequential circuit, so the encoding with shift registers. So it gives kind of an extra dimension of flexibility in the code design. They have some nice properties, and this is the area that I've focused on during my research career. So now, during the 60s too, this code, which remember we cited as not being particularly attractive, but the fact that it had only 6 information bits, which, again, for those of you that know coding, it had only 32 code words. It's a low-rate code. They were able to design a so-called soft decision decoder. It was just a correlation, basically did correlation with the soft values, sample values coming off the matched filter. Didn't have to quantize. It was feasible to do that in a hardware implementation. And that gave these a nice advantage. This code was used on the Mariner space mission that went up in the late 60s. And it was able to take advantage of a almost 2 dB gain, coding gain advantage compared to the hard decision version. And this is typical. If you can implement a decoder to take advantage of soft decisions, you can do better than, about 2 dB better than a code which uses hard decisions, or a decoder that uses hard decisions. And then also at this time, there was a very interesting class of codes called low-density parity-check codes. Bob Gallagher at MIT did this in his PhD work in 1962. And this is a particular, do I have the bullet on this? Yes. It's a so-called, he invented so-called regular low-density parity-check codes. 504 here is the block length. Why did I pick that one? Because that's what he was able to implement, the software simulation, 504-bit length code at that time. And you have exactly, it has a parity-check matrix. If you don't know what a parity-check matrix is, again, you have to take the coding theory class. It has exactly J1s in each column of a parity-check matrix and K1s in each row. And J and K are small numbers, so it's a low-density matrix. And one of the nice features of this is there is a soft decision decoding algorithm. Basically, it's essentially belief propagation iterative decoding algorithm, which has lots of other applications other than just encoding. But he was able to introduce us, he had a practical, at least it could be implemented in software at that time, soft decision iterative decoding algorithm for these codes, and the performance was quite good. And the amazing thing is, almost everybody forgot about this, including Gallagher. I mean, there was almost nothing done with these codes for another 30 years, and we'll see that. I don't know whether I don't know the reason. My suspicion is they were thought to be complicated, but that's actually not true, because they have some complexity. They have a decided complexity advantage. Maybe they're just too complicated to understand. But this had about a 6 dB coding gain already. And then, now this is maybe part of the explanation, is that convolutional codes, so-called long constraint length convolutional codes, this one had a constraint length of 31. So you can think of a shift register with 31 stages for encoding, so-called quick look-in code. Those became very popular also at the same time. They also could make use of soft decisions. And in terms of what could practically be implemented, they were quite good, maybe even a little better. That the LDPCs were considered to be a little more complicated. But people were excited about these codes. And these are some of the people: Bob Fano at MIT, Kamil Zagangarov in the Soviet Union, Fred Jelinek at Cornell, Irwin Jacobs, who went on to found Qualcomm and I guess Qualcomm Stadium now, and just won the IEEE Medal of Honor, by the way, this year. Was also worked a lot in this area. Rolf Johannesson from Sweden is another one who worked a lot on these kinds of codes, and they were used on the Pioneer space mission. It was a Jupiter flyby mission in the late 60s, and these codes were used for that mission. So yeah, for deep space coding applications, it got almost 7 dB. You'll notice you're right up against that cutoff rate. And this is kind of what people thought we weren't going to be able to do any better than that. Turned out to be incorrect. Also at this time, Andy Viterbi, who was a kind of co-founder with Jacobs of Qualcomm, much later in his career, this was early in his career, developed a way of, although we didn't know it at the time, as in many cases, developed a way of actually doing maximum likelihood decoding. Most of the decoding algorithms that are developed are not optimum decoding algorithms, they're suboptimum, just for implementation reasons. The maximum likelihood or map decoding methods, typically very complex. But for short constraint length convolutional codes, he developed an algorithm which came to be known as the Viterbi algorithm. He didn't call it that originally, which you could actually use maximum likelihood decoding. So, and again, it was soft decision. So these codes also became very popular, even though they actually lost performance because the Viterbi algorithm could only be used with small constraint lengths because it has a number of states associated with the algorithm, which grows exponentially with the constraint length. So it's only practical for short constraint lengths. So something like this, sequential decoding of long constraint length codes, you could use more powerful codes and you could get better performance. But there was a lot of practical advantages to using the short constraint length codes, and you'll see in a minute another reason why these became particularly popular. So it gained about 5 dB. Very simple short constraint length convolutional code. Again, for those of you that know something about coding, this constraint length 6 needs to be decoded on a 64-state trellis, 2 to the 6 states. So If nu gets too much larger, then the size of the trellis gets too big, and it's impractical to decode this way. But this was another very nice advance. Now, what came along at about the same time was work by Dave Forney at MIT on something called concatenation, just the combining together of two codes. And a diamond in the picture, so we have squares for hard decisions, circles for soft decisions, and diamond indicates this concatenation construction. A lot of concatenation has been used a lot, and we'll see it in some of the later slides. So it denotes the concatenation of more than one code to obtain a more powerful code. And so what Forney's work did is, it was his PhD thesis in 1966, but it was also there were lots of versions of it. So the version that came to be really popular was the concatenation of one of these short constraint length convolutional codes with Viterbi decoding, one of these guys, concatenated with the so-called inner code, and there was an outer Reed-Solomon code, one of these guys, was adopted as the CCSDS standard for NASA deep space and satellite communications. And so what this lost compared to the long constraint length code, it could regain with concatenation. And since the combination of a short constraint length convolutional code with a Reed-Solomon code was considered somewhat easier to implement, I think, than the long constraint length convolutional codes. There were some practical advantages for doing this. So this became kind of the standard in some sense. Now I'm going to jump ahead to 1978. And remember I said that up until this time, people felt that this was where coding, you would have your advantage, and people didn't really see how to do it for higher spectral efficiencies until, and there was a whole group at Bell Labs that was devoted to try, because Bell Labs is obviously interested in developing higher speed modems. And to get higher speed modems, you need to use bigger signal constellations. And if you wanted to benefit from coding, you had to design codes which would give you coding gains with bigger signal constellations. Nobody could figure out how to do that. The group at Bell Labs, which had formed around that problem in the late 60s, was actually dispersed, and they went on to more profitable areas. And then Gottfried Ungerbeck at IBM Research in Zurich figured out the right way to do this, and it's called trellis-coded modulation. It takes a high rate convolutional code, rate k over k plus 1, like maybe 2/3 or something, or 3/4, and does combined modulation and coding using an idea called set partitioning. And instead of lowering the, so here you want a bandwidth efficiency or spectral efficiency of 2 bits per symbol, the coding, instead of using a code with QPSK, which would lower the bandwidth efficiency like all of these, Ungerbeck had the idea of expanding the signal set to 8 PSK and then coding with a rate 2/3 code to get you back down to the spectral efficiency that you started with. So compared to, and there's a similar method that developed about the same time by Hideki Amai in Japan that was based on a so-called multi-level approach, okay? Similar but different, but there were advantages and disadvantages to the two different ways of doing this. So in contrast to all of these kind of codes where you start with a binary alphabet and you code on it and you get a lower bandwidth efficiency, trellis-coded modulation and multi-level coding provide a gain in power efficiency without a loss in bandwidth efficiency, because they expand the signal set before they code, and the gain in power efficiency comes from this clever way or ways of combining coding and modulation. And so they're able to get like 2.5 dB coding gains out of the basic Ungerbeck code, which just used a constraint length 2 convolutional code. So very simple to decode with a 4-state trellis, as we talked about with the Viterbi decoder. And the multi-level scheme typically doesn't do quite as well at moderate bit error rates. At lower bit error rates, the multi-level scheme can do better. Okay. And you can do more complex. If you use constraint length 6, you can get bigger coding gains. Again, as you add to the complexity of the code design, you can improve the coding gain. I mean, raising the constraint length of a convolutional code is analogous to raising the block length of a block code. So longer lengths, according to Shannon, are going to get you more coding gain. Okay, now we jump to 1988. There was, in the 80s, there was a, now again, I said it's hard to do a Viterbi decoder with with a very large constraint length. Well, Oliver Collins, and I just got rid of Oliver there, okay, developed as part of his PhD thesis at Caltech a so-called big Viterbi decoder, which actually could do full maximum likelihood soft decision decoding on a constraint length 14 convolutional code. So this is not the kind of decoder that you're going to get as a prize in a cereal box or anything like that. I mean, this is an expensive piece of equipment that could only be used in a government research project where there's plenty of money to pay for it. So it's not something that has ever come down to the commercial level. But for the Galileo space system, they were actually able to concatenate this much bigger convolutional code with Reed-Solomon codes, and for the first time really moved beyond cutoff rate, and people started to question, because this, even though it was complex, it could still be built. It was practical. So this idea that cutoff rate was some kind of a practical limit started to disappear here in the late 80s. Bob McLeese at Caltech was Oliver's advisor and has contributed much over the years to the design of codes for deep space applications. In fact, if you went to most of you were probably too young, but some of you may have been, I know Sasha was at the, and Shannon also probably at the ISIT symposium in Chicago in 2004. Bob was a Shannon lecturer, and he gave a nice, and Prakash was there too, gave a nice summary of, the progress of deep space communication. Okay, so this is the... Now also during this time there was still a lot of activity in the more spectrally efficient range. Multi-dimensional signal sets came into play where you'd use 2 copies of an 8 PSK signal, say, as one symbol, and you'd code with maybe a rate 5/6 code instead of 2/3 with 1 copy of 8 PSK, able to get fractional bandwidth efficiencies. So again, primarily for modem applications, people were interested in pushing these spectral efficiencies higher and higher. And Victor Way at Bell Labs was one who developed a large number of codes for modem applications, and also Rob Calderbank, who just won the Hamming Medal, just announced, and Neil Sloan did a significant amount of work in this area also at Bell Labs. So the Victor Way code became one of Victor Way codes. It was actually a nonlinear encoder because there was a requirement that the code be invariant to rotations of the signal set. Otherwise, if you're using 8 PSK and your demodulator locks onto the wrong phase, if you don't have a rotationally invariant code, that can cause catastrophic error events. So it was important to design the codes to be so-called rotationally invariant. And he found a way to do that with which just means in a in a shift register implementation, instead of using all exclusive OR gates, you may use an AND gate or an OR gate or something like that, something that isn't linear. And this V.32 standard, modem standard, achieved about a 3.5 dB coding gain with no loss in bandwidth efficiency. Now, 98, again, the early cellular standards were primarily used short constraint length convolutional codes with soft decision Viterbi decoding, GSM, and I guess this is IS-95. These were perfect. I mean, for voice, you don't need the really low error rates, and you needed something that was simple to implement. So these were the best choices there. And there were a lot of work in the 90s on going back to some of the old algebraic codes and try to design soft decision algorithms, because the original decoding algorithms were pretty much required hard decisions, so to try to get that soft decision gain. And this was a very important research topic in the 90s, Shu Lin again. And again, there are lots of people here, and this is not comprehensive. Jack Wolf and Frank Shishang with a soft decision version of the Golay code. Marc Fossorier with a soft decision version of a BCH code. And Ralph Cutter and Alex Vardy were two people who worked on soft decoding for Reed-Solomon codes, which is still a very interesting research area. Now, in this time also came sometimes people refer to this as the Big Bang. We really struggled to get beyond the cutoff rate here. We had to use this quite complex Viterbi decoder. And then three Frenchmen, Claude Barou, Alain Glaviot, and Gerard Bataille. Well, these two, Gerard was kind of the grandfather, if you like. He had some of the original ideas that led to this invention by these two guys of something called a turbo code. And turbo codes basically use a large pseudo-random interleaver, a scrambler, to concatenate in a somewhat different way from Forney's original idea, in a different way, but it's still concatenation, two short constraint length convolutional codes, and they perform iterative decoding. BCJR decoding is just map decoding on these two short constraint length codes. So they're able to use maybe constraint length 4 or something, simple component codes. Sometimes the smaller the constraint length, the better in this design, like you would use out here in these cellular standards, but combined in a way with just a scrambler that allowed this tremendous improvement and getting very close to capacity. It's interesting, these two gentlemen were not really coding theorists. So what were the rest of us doing? We were all asking that question ourselves. But, you know, the background was, I shouldn't say this because I know there's some control people in here, but the background, at least Claude, was control. Okay, and there's an aspect that in the iterative decoding, there is feedback in the decoder. So there were some ideas from this area. But sometimes when you're in an area too deeply, there are certain assumptions you make about what can and can't be done. And you live with those. And you should always, in research, you should always question your assumptions. Do I really need this? Do I really need this? You know, there's always, if you can remove assumptions, you can remove restrictions, and there's always new ways to look at problems when you do that. And these guys had a very clever idea, although they will admit, partially they stumbled onto it. So they couldn't explain themselves why the performance was good, but they had the intuition primarily with the iterative decoding from ideas from control. They kind of stumbled onto the code design, but anyway, that's a longer story. So this notation here, K denotes the interleaver length, the scrambler length, which turns out to be the block length. Even though they use convolutional codes here, the resulting system is a block code. And this P here just denotes the number of iterations that the decoder had to do. So this original design was 65,000 bits long, 18 iterations. Now, yeah, 65,000 bits long, you're getting to the point, you're getting a length which you can get close to capacity, according to Shannon. Now, why didn't people do that earlier? Well, there was nothing practical that you could do with that block length. And this concatenation of two short constraint length codes was just a big scrambler. It was very easy to do. So they figured out a way of getting these long block lengths with a very simple implementation. And they were, this Galileo system, which is, this is much more complicated to implement, still had left about 2 dB short of capacity. The turbo code at the same bandwidth efficiency left less than 1 dB. So with a much simpler system, there was quite a bit of gain. And now one thing with these codes, this one at about 0.5 dB, if you used, well, kind of I've said this, if you use a shorter interleaver, shorter block length, you don't get that much gain. You lose a couple of dB. And also because these turbo codes are actually, in some sense, a form of a low-density parity-check code, people at this time went back and kind of rediscovered low-density parity-check codes. They realized the connection, and these are some of the early people. Based on looking at a graph-based representation of these codes that had been originally introduced by Michael Tanner, who would be a good person to, he's here in Washington now, would be a good person to have over for one of these talks. So the LDPC codes at this point look somewhat competitive also in terms of their performance. And then Joachim Hagenauer in Munich developed a version of turbo codes based on a kind of a product code description using block component codes instead of convolutional component codes. At that point, it was the closest code to capacity, about 1/4 dB. Now, one thing that happens here when you go to 10 to the minus 10 and you look at this turbo code, at 10 to the minus 10, it didn't just move over a little bit, it loses a lot. And that's a characteristic of turbo codes, in that for moderate error rates, they're terrific. For very low error rates, they're not very good. So this code lost over 5 dB compared to its performance at 10 to the minus 5 and 10 to the minus 10. And by contrast, this LDPC, when you go from 10 to the minus 5 to 10 to the minus 10, lost only about 1/4 dB. So people, the tendency now shifted a little bit more towards low-density parity-check codes because they seem to be more robust in the sense that they could get good performance at moderate error rates and also at lower error rates. Rajiv Laroya was the one who invented designed the V.34 coding, the code for V.34, which used a shell mapping technique to get about 1 dB of what's called shaping gain, constellation design, in addition to the coding gain. So this wound up in the ultimate modem standard with about a 3.7 dB gain. Now the last decade here, there was, of course, the obvious thing was to try to apply this turbo and LDPC to the more bandwidth efficient range, and Sergio Benedetto in Italy and Dariusz Divsalar at JCL invented something called parallel concatenated trellis coded modulation. And there was a so-called bit interleaved modulation, which could be used with bit interleaved coded modulation, which could be used with an LDPC code. Ezio Biglieri and Giuseppe Cair, among other people. Effie Zahavi also looked at these kind of designs. And again, it's for trying to apply these powerful codes to more bandwidth efficient systems. And Johannes Huber at JPL in Erlangen in Germany. Remember the multi-level scheme that I talked about, IMI's scheme. Johannes applied that, combined that with turbo codes to be able to get, again, some excellent performance at high bandwidth efficiencies. And then Rudy Urbanki and Tom Richardson at Bell Labs at the time discovered the design, an irregular, remember I said Gallagher's was regular, but they discovered an irregular LDPC code design, parity-check matrix whose row and column weights can vary. And by doing that, they were able to get essentially to capacity with a low-density parity-check code. And the complexity of low-density parity-check codes just grows linearly with block length. So this is if you can tolerate the delay, these are long codes, you can essentially get the capacity of LDPC codes. That's pretty close. That's a 10 million bit block length. And then there's also, for more practical designs, these random LDPCs are a little difficult to implement. And Shu Lin and Michael Tanner, among others, have worked on so-called quasi-cyclic versions of LDPCs, which are the kind of design that's actually going into most of the modern standards, like WiMAX and such, DVB. And then, just in the last few years, Erdal Erikan in Turkey came up with a new design, which is also is capacity achieving design, called polar codes. Here I've given a point for a particular block length of polar codes. And polar codes are the latest thing in coding theory, and they're based on the principle of polarizing a set of n independent copies of a discrete memoryless channel. And again, if you take Professor Barg's class in information theory, you're going to learn all about polar codes. So that's kind of the story. Now it's and I know there's another seminar, so I won't be offended if people leave. But I have about another 5 or 10 minutes of somewhat, hopefully, lighter material. So thinking of what I could do in Washington, D.C., I thought it might be interesting to, particularly since we just had an election, to ask some of the political players in this area what their favorite code was. So I've been doing this over a period of the past few years. Whenever I see one of these individuals, I quiz them about what their favorite code is. So I've kind of developed the following results. So, I was one step ahead of myself. There's also spatially coupled codes, which I talked about yesterday. And these also are capacity achieving like polar codes. And Camille Zagandgroff and Mikhail Lentmeyer, Sweden, Germany, now back to Sweden, Russia to Sweden, Germany to Sweden, were the early workers in these spatially coupled codes. Okay, so political views on coding theory. This was President Bush, who was president from 2000 to 2008, said, well, W, what is your, which code do you like? And he said, well, I always liked this one. Okay, and I said, yeah, it's not a code at all, that's just uncoded. I mean, what was your favorite code? And he said, well, coding gets you closer to the axes of evil, so he didn't want to deal with any kind of coding at all. Now, then, of course, 4 years ago, I also talked to Hillary Clinton, who was a presidential candidate there and maybe in the future. And she liked this code. I mean, you know, this is that 10 million bit code, which is 0.0045 dB from capacity. I said, well, okay, that's a great code. I mean, what particularly attracted you to that code? And she said, my race with Obama was asymptotically close, 0.0045 dB. Okay, so that was her reason. Then we have Vice President Biden, still Vice President. And I said, Mr. Biden, what was your favorite? He said, I like this one. I said, well, you know, the rate is low. I mean, the rate is 0. And he said, well, when I speak, there's no information content anyway. So. And then Governor Palin, who was also a vice presidential candidate 4 years ago. So I said, what was your favorite code? Well, you know, she picked the polar code. I said, why the polar code? Well, I'm from Alaska, you betcha. I just love those cute little polar codes. Okay, and particularly that one. All right, and then, you know, so then there was Senator McCain, who was he's usually photographed from the other side, but he was the running in 2008 for president, of course. And I said, what do you like, Senator? And he said, well, I kind of like this one out here. And I said, well, that's, yeah, okay, but that you get a loss in bandwidth efficiency and a loss in power efficiency. So kind of why is that your favorite? And he said, well, I'm a real conservative. He said, look how far to the right I am. So he was trying to convince some people in his party that he was really conservative. And then, of course, we had President Obama. And when I talked to him, this is before he was President Obama, but I said, he liked this one. I said, well, come on. I know you're from Illinois, but you can't do this. And he said, well, you can too, hope and change. And he proved it by citing a reference to the Audacity of Hope, which was published in 2007. So, of course, way beyond capacity there. Then I had a little fun with some of the Republicans. The rest of it's all Republicans because there were no new Democrats running this time. So Governor Perry, so he, what did you like? Well, he said, this one, this parallel concatenated trellis coded modulation, like that one, and I like this one too. This BICM. Yeah, I can't remember the third one, he said. So he lost track of what was his third best choice. Now, you may or may not remember that the Republicans had Herman Cain also running for president, who was a pizza guy. Okay, I like pizza guys. Actually, my wife's family is in pizza business. These spatially coupled codes, actually I didn't dwell on this, but they get their good performance by taking a convolutional code, which is kind of continuous, and doing a termination of the code or the graph at the end. And Herman liked that one because he said the Herminator likes to terminate. Okay, then I had Ron Paul, Representative Paul, okay. And he's kind of a libertarian from Texas. And we asked him, and he said, I don't have a favorite code. I'm going to eliminate NSF, so we won't need this kind of research anymore. Okay, obviously I wasn't too thrilled with that answer. And then Mr. Gingrich also ran on the Republican side, and he liked the Galileo code. And he said that NASA code will help me colonize the moon, which, if you remember, was one of his programs. And then, of course, we got to Governor Romney, and he said he kind of liked this shortened BCH 153 code, 100 bits, 53 information bits. I said, well, why that one? Well, its information rate is 53%. He said the other 47% is redundant. It doesn't add anything. Okay. And then, okay, I think this is the last one. This is the Representative Ryan, who ran with Romney. And he liked the turbo code. He really kind of liked that one. I said, well, why did you pick that one? It's good code, but why in particular? And he said, well, this is a good one for pushing Granny over the cliff because it's got a bit error rate curve, which is a sharp fall off like that. So I can just send Granny right down the cliff of the turbo code, bit error rate curve. Okay, so that's I like to do that. I don't know whether the audience likes it, but so kind of what's developed, the major kind of themes in coding throughout the first 6 days of creation. There's algebraic coding we talked about, convolutional shift register codes, then the Viterbi algorithm, which allowed you to do maximum likelihood decoding of these codes. Then the trellis coded modulation, which allowed you to get coding gains without bandwidth expansion and for the modem applications. Soft decision decoding of block codes, turbo decoding, iterative decoding, LDPC codes, which I didn't really get into this at all, but the kind of it's a class of codes on graphs, of which LDPC codes are maybe the prime example, and that's been a major theme in the last 10 or 15 years. And then more recently, these polar codes and spatially coupled codes. And these are just some of the people that you saw during the presentation, and some that you didn't see, I think. And then what happens on the 7th day of Genesis? Rest, right. But actually that's not allowed for students, okay? Sometimes it is for tenured faculty members. I mean, this is just a hodgepodge of things that are still of active interest in coding. There's still a lot of kind of modern code designs, algebraic geometry codes I didn't even talk about. There's these rateless codes for internet applications, space-time coding for MIMO, and a number of interesting new code designs typically for specialized applications, though not. The Gaussian channel problem, as you see, has kind of been solved. Okay, depending on, okay, if you want really low error rates, then there's still work to do, but you can get the capacity on the Gaussian channel. System design issues. So there's lots of interest in how do you design efficient decoders from a hardware point of view. Even analog decoder implementations have been discussed. Encoding sometimes is an issue with low-density parity-check codes. There's always applications like joint source and channel coding, unequal error protection, things of this nature that are application-driven that are still largely unsolved. And then these are just, again, a list of some of the applications, even things like power line communication, quantum coding, coding for flash memories, and again, the internet applications, network coding, packet erasure channels, and some of the standards in some of these areas, wireless, DVB, cable transmission, etc. So it's still a very active area. It's moved somewhat from the trying to reach capacity on the Gaussian channel into try to find good ways of applying coding in lots of different applications, and with particular attention paid to implementation costs and complexity. So I think that's the end of the story.